I welcome you all, everyone. Good evening. So, as of now, I think we are having only one student in the meeting. Let's wait for another 5 minutes. After that, we will start for today's class. Hi, Varun. How are you?
Yeah, sir. Good. I'm good. How are you, sir?
Yeah, I am fine. I think you are after so many classes, I
Yeah,
think. Yeah.
yeah,
From
yeah.
last two, 3 weeks, you were not there.
Actually, I was in first 2 to 3 weeks, but after that, I was unable to cope up with my office and these classes. But I was submitting my assignments and all those things. So
Okay.
later on, I understood that it's like all these are new topics which are coming. It's like all these thermoelectric generators. It's like okay, till 2 weeks back, it's fine because as I'm a mechanical student, I was able to simply do the things
Yeah.
easily. But from
Yeah,
last
right.
assignment, I understood the depth in it. So I thought, okay, by this week somehow I should make time to attend this. Yeah, I'll be
Okay,
regular
okay.
from now. I'll be regular from now.
Yeah.
It's needed for me from now.
Yeah, nice to hear it.
Yeah, yeah. Main
Yeah.
problem is with the office timings and the weekend wala things, all those things mainly.
Yeah, correct, correct. Because I think from last 2, 3 weeks only 2 or 3 students are joining.
Oh, okay.
Yeah, let's see today how many students are there. Let's see.
But the main problem is I have able to complete only 3 video lectures. So I was actually thought of completing today, but I was unable to cope up in the office also.
Okay.
So I thought, okay, at least I will have some review on that thermoelectric generator part at least.
Yeah. Okay, let's wait for 2 more minutes. After that, we will
Yeah,
start. Yeah.
sure. Yeah. Then first of all, it's Happy Engineers Day, Amit.
Yeah. Same to you also. Yeah.
Yeah,
Thank you.
thank you.
Thank you.
So how is your work going on? It's everything fine?
Yeah. Yeah, everything is fine. Work is going fine. Let me reshare the screen. Actually, just I have made some changes. Mm,
Okay.
minute. Yeah, is my screen visible?
Yes, yes, it's visible.
Okay, okay. So, okay, I think we have waited enough. So let's start with today's class. So, good evening, everyone. So, my name is Amit Kumar Sharma, and I am the course TA for this NPTEL course, Energy Conservation and Waste Heat Recovery. And today we are in our live session number 8 for the week 8 course content. So let's start with the some basic questions, and after that we will discuss some concepts. Let me start. Okay. So the first question is the thermoelectric generator and thermoelectric refrigerator work according to which principle basically? So the one is Peltier and Seebeck effect respectively, then B Seebeck effect, then Peltier effect, and D Seebeck and Peltier effect respectively. So a basic theoretical question. Take 2 minutes to think about it and let me know the answer. Today we are having two students. One is Varun and hi, who is there else? Because your name is not written here, it's showing only guest. Okay,
So I
maybe
think it's option D.
okay. Option D, Seebeck and Peltier effect respectively. Yeah, it seems so. Let's wait for another 1 minute. So basically, thermoelectric generator, TEG. So what is TEG basically? I think we have covered in our last 6 classes.
Yes, yes, it's
So
thermoelectric
what is
generator.
TEG, Varun? Any idea?
Yeah, it's thermoelectric generator which works on the Seebeck effect. If two non-similar metals are made as two junctions, and if we heat one junction, if we create some temperature difference, automatically there
Okay,
will be some kind of EMF generated.
okay, yeah.
Such kind of thing happens, thermal generator. So it works on Seebeck effect, and Peltier effect is like so they said that it's a kind of there is a Joule heat, so excess of heat has to be rejected out. I think that is kind of a Peltier effect. So that thermoelectric refrigerator works on it. It's like rejecting pulling and rejecting heat. Rejecting heat, that's why it's Peltier effect.
Yeah, yeah, correct, correct. So basically, just TEG, like just overall, we are just directly converting the thermal energy directly to the electrical energy.
Hmm.
Yeah, TEG. Because I think in last class, uh, one was having doubt that we are converting thermal to mechanical and then electrical. So in thermoelectric generator, we are directly converting thermal to the electrical. Okay, let's check the answer. So correct option is D. So the thermoelectric generator works according to Seebeck effect, where temperature difference is converted to electrical energy. So directly just we are converting the effect of temperature, or you can say thermal energy, into electrical energy using Seebeck effect. On the other hand, thermoelectric refrigerator works according to Peltier effect, where voltage difference or electric energy is applied to create temperature difference.
Temperature difference.
So basically, here we are applying the voltage. So like you can see in our refrigerator, we are providing the electricity to, to operate the refrigerator. So basically in refrigerator, we are extracting the heat from the cooler environment, the inside part, because the refrigerator inside is the cooling area, you can say. So we are extracting heat from the cooling area and we are putting it to the, like from the outside the refrigerator to the heated area. So that can be done by only the electrical energy. So we are supplying here the electrical energy. On the other side, in the Seebeck effect, we are generating electricity from temperature difference. And if you want to look into more, you can go back to the previous week's classes where we have discussed about the complete theory about the TEG, thermoelectric generator. Okay. Figure of merit Z for a TEG is a function of, so the temperature difference between the hot and cold side, the material properties, the magnetic properties, and all of the above. Let's think about it.
So it's option B, material properties.
Option B. So yeah,
But
it seems so.
my doubt is like, okay, it's like merit is ratio of Seebeck effect by summation of the thermal conductance and the resistivities, right? It's like, sorry, resistances. So if that is the case, we'll be having the geometry also as one of the function, right? In
Okay.
resistance, we'll have resistivity into area by length. So
Yeah.
so I think so. It's geometry also should be there, but here in options it's not provided. It might be. Am I right or not? Just correct me if I'm wrong.
Because actually I have to also see that I'm not remember the exact formula
Okay,
for
okay,
the figure of
okay,
merit.
okay. No issue.
Yeah,
Actually,
yeah,
in that video lecture also they said that it's a function of material properties and geometry. That's what
yeah.
I heard.
Because if resistance is there, then the length and area will take
Resistivity,
part.
area,
Yeah,
length will come
resistivity.
into
Yeah,
picture.
yeah, yeah.
So
So actually they are not in option. That's why maybe the only option B is correct.
material properties, yeah.
Yeah, yeah. Because there is no geometric property option is there. Because if resistance is coming, so yeah, sure. So there will be also
Hmm.
length and area will be there. So basically dimensions will be there. So geometry properties will be there. But they are not an option. So we have to
Yes, they are
select
not
from
an
the
option.
options
I think
only.
so.
Let's see the answer. So figure of merit is dependent on the thermal conductivity, Seebeck coefficient, and electrical resistivity, which comes under the material properties. Okay, so the option B is correct. And also the thermal conductance and electrical resistance also depend on dimensions. So yeah, yeah. Basically, it's also depend on the geometry. So dimension is also there. Okay. So basically, they are taking this dimension property into the middle part itself because this conductivity, Seebeck coefficient, and electric resistivity are comes under the metal properties, and these properties are dependent on the dimension.
Dimensions, yes.
Yeah. So basically, if we are saying the metal properties, then we are considering all these thermal conductivity, Seebeck coefficient, and electrical resistivity. So they are already including the dimension. That's why they have not mentioned it separately because they are the
Okay.
integral part of these. So they are come under the material properties.
Okay.
So basically, figure of merit, you can say the efficiency for the TEG. Okay, so figure of merit jet can you consider like efficiency for the TEG. It depends on the material properties and basically on thermal conductivity, Seebeck coefficient, and electric resistivity. For the complete relation, you should refer to the class notes where you can see the complete derivation for this. Come to the next question. So again, G, the figure of merit value is hard to increase as it is difficult to get material with. So Z value is hard to increase as it is difficult to get material with option A, high thermal conductivity and low electrical conductivity, high thermal conductivity and high electrical conductivity, low thermal conductivity and low electrical conductivity, option D, low thermal conductivity and high electrical conductivity. So take 1-2 minutes about it.
It's option D, high electrical conductivity and low thermal conductivity.
Okay, it seems correct. Let's wait for another 1 minute. Okay. So the answer is D, because the expression for Z shows the electrical resistance and thermal conductance in the denominator. So the point to be noted that electrical resistance and thermal conductance are in the denominator. So hence to increase G, we need a material with high electrical conductivity and low thermal conductivity. Such materials are hard to find naturally. Okay, so as these are in denominator, so if we want to increase G, then we need material with high electrical conductivity and low thermal conductivity. So the denominator value will decrease and the G will increase. Okay. If the Rp and Rn are equal to 1.5 and 1 ohm respectively, then which of the following is true? Option A is external resistance of 2.5 ohm results maximum efficiency. External resistance of 2.5 ohm results maximum work output. External resistance of 2.5 ohm results both maximum efficiency and maximum work output. And the external resistance 0.5 ohm results maximum work output. First of all, you should know that what is the external resistance formula. Basically, what is the Rp and Rn?
So it should be 2.5 ohm Results option A. Why? Because for the maximum efficiency, the M value, the ratio of the external resistance to the resistances of the P and N semiconductors should be equal to 1. So its summation it's like, so RL should be equivalent to RP plus RN. That is the
Yeah.
case to 1.5 plus 1, it's 2.5.
Yeah, nice. Let's wait for maybe 1 minute if anybody else wants to answer or discuss it. Varun, when is the exam? Do you have any idea?
It's on October 28th.
Okay, October 28th.
It's like 5 more weeks to go. It's like, yeah, it's like a 12 week session, I think so, right?
Yeah, 12-week session, and at the end, I will take one more class to sum up all the 12 weeks actually.
Okay, okay.
Yeah, you can say there will be one revision class, you can say. So in that, we will discuss all 12 weeks, maybe some concepts, and we can also
Okay.
discuss something else also. So there will be
So
a
there are
summary
revision
class.
classes also.
Yeah. One class will be there after 12 weeks.
Okay.
So total
After
13
12
class will
weeks.
be there.
Okay. Maybe by the time we should be ready with all the things. I don't know. It's like all the first weeks were gone already. So we should recap. Okay, it's fine. It's a mechanical thing. It's fine. But after
Uh,
week 8, it's again completely new concepts again.
yeah. Okay, let's see the answer. So answer is A. So basically, when the external resistance is equal to the sum of resistance P, that is Rp, and N type, that is Rn. So that is RL equal to Rp and Rn. So it results the maximum work output. So for the maximum work output, the external resistance should be the sum of the P resistance and N resistance. So that will be result in maximum efficiency. So it will be 1.5 plus 1, 2.5. So it will deliver the maximum efficiency. The efficiency of a MHD process is limited by, we have 4 options: length of the duct, ionization potential of the gas, below 2000 Kelvin, the gas molecules become neutral, thermal conductivity of the gas.
Oh, I think so. This question is entirely out of my box now.
Yeah. So its MHD is basically a magneto-hydrodynamic generator. It's quite new for me also, actually.
Okay, actually, I should have watched those videos and come to this session. But
Yeah.
due to the time constraint, I was unable to manage today.
So basically, the MHD is magneto-hydrodynamic generator.
Okay.
So at the end of this class, like we are having around 10 questions. After that, we will discuss these all technologies that have been taught in the class. Basically,
Okay.
just go through it. basically, MHD is a magnetohydrodynamic generator which transforms the thermal and kinetic energy into direct electricity. Okay. So the benefit is that there is no moving part. Basically, there is a magnetic field is there. Okay, and the ion and the ionization of gas will be there. So there will be basically you can say ions. So you need very high temperature for this to generate the ionization of the gases. Okay. And
Okay.
basically it is used for a topping cycle. Like like we have seen that normally if we are talking about the waste heat recovery, so we are using the bottoming cycle.
Hmm.
Okay, but this MHD is used as a topping cycle because it requires very high temperature. Okay, so first we will convert the high thermal heat, okay, to the electricity. After that we will use that gas, or you can say that heat, in the boiler to generate the steam and further to run the steam turbine or gas turbine or like any other cycles. So basically the main funda that why it is coming in the waste heat recovery topic, because today we are having like furnaces that can go up to 3000 Kelvin or up to very high temperature, but we are not using uh, but the turbine inlet is having some limits. Okay, so we cannot like the inlet stream of that is going to the turbine or in any like in any other equipments also they are having some temperature limit. We can go
Metallurgical
we
conditions.
yeah, we cannot go beyond some like maybe 1500 Kelvin or or 1900 Kelvin like that. But in the furnace, we can go up to 3000 Kelvins. We are having those furnace available in the market. So
Hmm.
that's why it is using as a topping cycle. So first we heat our gas to a very high temperature, then we will put the MHD, and that gas will go through MHD and generate some electricity. After cooling up to the required temperature, that will go to the other cycle. In this way, we can recover the energy that can be converted into electricity. That's why it is coming under the waste heat recovery topic. Let's see the answer. So the gas ionization potential is critical for release of electron. So this gas ionization potential is very critical. Okay. The ionization is lost below a temperature of around 2000 Kelvin as electrons combine with ions to form neutral molecules, which restrict the temperature gradient of operation. So basically, for this system to work, we need ions, not complete molecules. And ions will be generated if the temperature of the gas is more than 2000 Kelvin, or you can say nearly 3000 Kelvin. So we require very high temperature for this. Okay. So you can say the efficiency will be depend on the ionization potential of the gas, and below 2000 Kelvin, the gas molecules become neutral. So if this is the case, then the efficiency will be come to zero or the system will not work. And this is also very important. B is also very important, okay? Because this is the potential that is defining the efficiency of MSD process. So option B and C are correct. So a TEG, a numerical, a TEG is made of electrons, made of elements with the following properties. We have given properties alpha Pn at 1250 Kelvin also 0.002, and the rho P 0.01 ohm centimeter, rho N 0.012 ohm centimeter, Kp 0.02 watt centimeter Kelvin, Kn 0.03. Calculate the value of G at 1250 Kelvin. So first of all, try to remember the formula for G. You have given all the values, just need to remember the formula. If you know the formula, you can directly know the answer. So let me give you the hint. The formula for V is alpha square on so P to N and Kp plus K.
Yeah, it's option B 0.0036.
Now put all the value in the formula. Let me know the answer. We have one answer as B 0.00363. Let's wait for one more minute. Now you have formula, you have values. Now put all the values in the formula and just calculate it. Take care of units actually. Units are very
So
important.
I have a doubt, Mr. Amit. It's like I have seen in some of the previous assignments also. Suppose if I
Mhm.
take this formula, it's like alpha square by resistances, summation of resistances plus summation of the thermal conductances. So it's
Yeah.
like that's the actual formula which they have shown in the video lecture or something, where that
Mhm.
resistance is equivalent to thermal resistivity. I mean resistivity into area by length. But they are not giving the dimensions of the any material or something here. It's like we have to assume that as one,
Dimension.
because AP by
Okay.
LP should be there in the formula. So that AP by not only this one, it's like before assignment also in one of the assignments. So it's like they are not giving some of the variables values they are not giving. But if we assume that as one and if you are calculating, we are getting few answers. It's like I don't know whether am I doing mistake or the had a doubt.
Uh,
Now also it
ba-
has happened in the same way.
Basically, you can see these are like per centimeter, like you can say ohm centimeter, and also watt per centimeter Kelvin. So they are already like best calculated based on the unity, I think. That's
Might
why,
be.
yeah. So that's why this is the case. Because if you take the dimension, then it's going to be difficult. They are already taking care of it because they are, you can see the per centimeter or ohm centimeter. So they are incorporating the dimension part.
Yeah, obviously, correct. Why? Because it's
Yeah,
like ohms into area balance, so only centimeter will be 1 unit will be left. Yeah, correct.
yeah,
Yeah.
yeah, yeah. They're already taking part like the CP, the specific heat like kilojoule per kg Kelvin. So
Hmm.
we are taking the consideration of mass here, kg. So it like we can directly multiply the mass and we know the answer. Like similarly, like you can say the centimeter is there. So like L by A. So area is having two dimension, L is having one, so one will cut out and one dimension of the will be there. So that is taking part in the unit also. So the correct option will be option B. So you can use this formula and put all the values. The answer will be 0.00363. Which of the following is or are true? Option A, at absolute zero temperature, 0 Kelvin, Fermi energy is non-zero. Absolute zero temperature, Fermi energy is zero. Work function of collector is higher compared to work function of emitter. Work function of collector is lower compared to work function of emitter. Take 2 minutes to answer this. Okay. So basically, Fermi energy is a concept of quantum mechanics referring to the energy difference between the highest and lowest occupied single particle states in quantum system of non-interacting fermions at absolute zero temperature. So at absolute zero temperature, what is Fermi gas? Fermi energy is zero or non-zero? See the answer. Fermi energy is non-zero at absolute zero temperature. So option A is correct. And it will be the highest energy of that particular. So it will be the energy of the highest occupied single particle state at that point at 0 Kelvin. And the work function of a collector is lower compared to work function of emitter. So if there is a collector and there is emitter, then the work function of collector is lower compared to the work function of emitter. Okay. Let's go to the next question. In a power plant with hot gases coming from combustor at 3000 Kelvin, one can use a MHD, a TPV, and TEG. Before using the gas in the steam generator, what should be the order of this device along the hot gas path? Very good question. Take 2-3 minutes to think about it.
Sorry to disturb you now. It's like, what is TPV?
TPV is thermophotovoltaic energy converter, or you can say energy conversion system. So TEG we already know, thermoelectric generator, and MHD we already have like previously magneto-hydro thermo, like what is the name? I also forget.
Magnetic hydrodynamic
Yeah.
thermometer, something is there. So it's like, suppose as you said, it's like MHD, it should be active greater than 2000 Kelvin only. It's like, as the energy is around 3000 Kelvin, we can go with the MHD option first.
Yeah.
I'm sure about it,
Right.
so it should be D. It's like, as you said, about 2000 only the activation will happen there.
Yeah, about 2000 only.
Yeah. So then it's MHD, TPV, and TEG.
I have also mentioned that MHD we are using the topping cycle. So
Topping
it's obvious
cycle,
that, yeah, MHD will come first. So if we go through that concept, so directly we can, if we don't know about TPV, still you can answer because MHD is first, and MHD first is only in one option, option D.
Yes, yes.
Yeah. So this is also a good technique to answer. So you can check all the option and you know about one. So you are sure about that, then you can directly answer D. Let's wait for one more minute. Because for TEG also we know that thermoelectric generator that we can use the temperature difference to get the electrical power, to generate electrical power, and there is no like limitation that we require this much of temperature difference or this much of temperature difference because we've gone through it. So TEG basically also uses a bottoming cycle. So we also know that TEG will come last because we can use the exhaust heat, yeah, from the plant to generate the electricity. Okay, let's see the answer. Yeah, option D is correct because the MHD must be used first when the gas temperature is highest. For this, the condition is that gas temperature should be very high. It should be greater than 2000 Kelvin. So first of all, we have to use the MHD. Since it loses its ionization potential below 2000 Kelvin. Because for MHD to work, we need the gas in the ionization form. Okay. So we have to use it for more than 2000 Kelvin because below this temperature, the gas cannot be ionized. So MHD will come first. Thereafter, the TPV should be used as the emitter temperature functions above 900 Kelvin. So there is also a limit for TPV. The emitter should have a temperature of 900 Kelvin. Okay, above 900 Kelvin. Then only the emitter material can emit, like basically the thermal photovoltaic, like we know about the PV cell. Okay, so in PV cell we are using the solar radiation. So the solar photons are striking on the PV panel and they are generating electricity. But in this thermal photovoltaic, we are using thermal energy to strike on the photovoltaic cell to generate the electricity. So the emitter, so the temperatures for the emitter should be greater than 900 Kelvin. Then only they can behave like sunlight and they can generate the electricity. Okay, so that is the beauty of this TPV system. So like we are making the full of PV cells. So we are like the PV cell is feeling like he's that cell is under sunlight, but no, the cell is under a emitter that can emit some thermal energy. Okay, and that is more than 900 Kelvin, so that the PV cell can generate the electricity. That is TPV. The TEG does not have any temperature restriction and can work across any temperature gradient. Hence, it should be at the last stage. There is no temperature restriction on the TEG. Okay. So at IIT Delhi, uh, students are developing TEG cook stoves. So I've already told about this system. So basically, they are trying to recover the waste heat from the cook stoves because if the cook stove any idea about the cook stove efficiency? Any idea, Varun? Like
No,
suppose in
no.
uh, so basically the cook stove is having very less efficiency because most of heat is going in the ambient. So if we calculate, so the
So you're telling about cook stove. Cook stove in the sense it's
cook
like
stove, open cook stove like that we are using in villages or like that.
okay, got it. Yeah.
Yeah, not like the LPG cook stove. I'm talking about the conventional cook stove that can use the firewood and etc. Cow
Yes,
dung,
yes.
firewood.
Mm,
Yeah.
yes.
What is the efficiency for those cook stoves? Any idea? What do you think? Just
But
just make
why?
a guess.
Because it's like we take a guess. I I cannot say the efficiency, but yeah, as you said, major portion it's going into the ambient. It's like completely open. It's not like a furnace kind of thing. It's like open structure. So
Yeah, yeah,
which you're burning. So it will be, and you will be using. It will be taking more and more time also. So these
yeah,
all things
yeah.
will come into picture. So how they are using it as by TEG, how they are
So make a guess. First efficiency. What is the efficiency? Make a guess.
TEG efficiency, I think so.
No,
It's
no, no,
around
not
30
TG,
per.
not TG. Cook stove
No,
efficiency. What is cook
just
stove
I'm running
efficiency?
that. It's TEG efficiency is around 30% or something, I guess. Then it should be
Okay.
around 10 to 15%.
For cook stove?
Cookster only I'm talking about. It's like less than
Yeah,
TEG. It
yeah,
might be.
yeah. Correct, correct. So actually, cook stove are efficiency in the range of 10 to 25%.
Yeah.
So the most conventional one is having around 10% efficiency, and some cook stove they are having some like covered area and all. They are having up to 15, 20, 25% efficiency. So they are applying TEG on the outer layer. Suppose this is the inner layer of cook stove. Okay, so here you will place the firewood and etc. And outer side of this, you will put some TEG device. Okay, so they are putting like it. So this will use this temperature, this exhaust, this high temperature, and generate electricity. So that electricity is sufficient around to charge a mobile and small LED bulb, I think. Yeah.
Okay.
Yeah. So they are like increasing the efficiency, and they are also basically the aim is to increase the cook stove efficiency. In this, they are covering the cook stove. Okay. So they are also making the biochar also. You can, they are actually having one more compartment here, I think. Some kind of arrangement is there. So basically they are making coal also. You can see they are putting uh, some biomass in that. So due to that, this heat, some pyrolysis is acting, working there. So like they are having TEG and they are having multiple option in that cook stove.
Okay.
So this is under development. So further, like you can use this coal in the next cycle. So that is having more efficiency than the firewood.
Okay.
So yeah, it's very good technology. TEG is very good technology for decentralized locations, for rural locations. So the correct option is D, MHD, TPV, and TEG. I think Bill and Melinda Gates Foundation are doing very good work for development of cook stoves. They are providing various funding to various agencies to increase the efficiency of cook stove. Because because in India, like after the Ujjwala scheme and many government intervention, uh, we are using LPG cook stoves. But still in Africa, if you go, then there are Africa and many rural areas also in India also. So they are using the conventional cook stove. So that is actually not good for health, not good for environment. So that's why they are putting so much of money to come up with a design that can be like go up to 50% of efficiency.
So it's like cook stove efficiency you're talking about.
Yeah, cook stove efficiency. Yeah. So today, if you go into the market, so there are multiple design available for cook stoves, but still the cost, they are very costly. So the normal common man cannot afford that. So still we need so much of intervention in this area, cook stove area actually. Okay, let's come to the today's class. So question number 9 is for a combined cycle power plant with TEG as topping cycle and Rankine cycle as bottoming cycle. Calculate the Rankine cycle efficiency if TEG efficiency is 8% and the overall efficiency is 49.4%. So you have given, we are using the combined cycle power plant, okay? With T is a topping cycle, Rankine cycle is a bottoming cycle. So the efficiency have given TG 8%, overall 49.4%. So I think we know the formula for the combined cycle efficiency. Try to remember that formula. Let me know the answer. I think Sebaz have also joined the meeting. Hi Sebaz, how are you?
Fine, sir.
Yeah, today you are late.
Yes, sir. I'm traveling to my home. I joined by traveling
Okay,
from
okay,
college.
you are traveling. Okay, nice. It's good to see that you are traveling and still you are attending the class. It's good to hear. Yeah. So the formula for the combined cycle efficiency, you can say is like this. Maybe you can try to put the values and
Yes.
let me know the answer.
It's 45%.
45% C. So we have an answer 45%. Let's wait for another 1 minute. Actually, we are waiting for 2 minutes that because maybe someone is like going to see the live classes online. If they also want to solve, that's why we are taking 2 minutes every time. So that they have 2 minutes in the video to find out the answer. Okay, so let's see the answer. The answer is it will be 45%. Okay. So here overall efficiency is 49%. So it will be 1 minus, you can say 49.4. 1 minus, it will be 8. And 1 minus this. So if you solve this, then you will get the answer of 45%. A single device has a conversion efficiency of 15% over the available temperature range. Assuming efficiency to be proportional to temperature difference, what should be the resultant efficiency of a cascaded system having 3 such devices at equal temperature gradients? Okay, let's take 2 minutes. So basically, a single device has a conversion efficiency 15% over the available temperature range. So we are having some available temperature range, and we are using only single device. Then the efficiency will be 15%. And now you can assume the efficiency to be proportional to temperature difference. Okay. So what should be the resultant efficiency of a cascaded system having 3 such devices at equal temperature gradient? So we are having 3 such devices at equal temperature gradients. Now what will be the efficiency? Okay. So the answer will be D, 14.3%. Since conversion efficiency is proportional to temperature difference across each device, the efficiency of each stage in cascade system will be 5%. Okay. So the overall efficiency therefore will be 1 minus ns ka power cube.
So it's like the efficiency of each stage in the cascade system is 15% or 5%.
Because the total I think a single device having 15%. Okay. If we are converting it into 3 devices, so we are like taking like 5% of each device. I think in that case, in that way, is the 5% for each stage. Because if the for same temperature difference, the single device is operating, that will be giving 15%. Okay, if temperature range is there. If we are assuming 3 steps, so now each step is 5%, 5%, 5%. But we are using 3 devices now.
Okay,
So
got it.
that will affect the overall efficiency. Okay.
Okay, sir. Okay, got it.
Yeah. Okay. So the overall efficiency will be 1 minus the ns, the system. Okay, it will be coming to 0.142, 14.26%. Note that cascading actually reduced the efficiency of here instead of improving. So you can see if we are doing the cascading, the efficiency is decreasing. Okay, earlier it was 15%, but if we are using 3 stages, then it is only 14.26%. So we have seen 10 numericals today. Okay. So I think first is the thermoelectric generator. Okay. If you have any doubt, let me know. After this, we are going to discuss some concepts. Okay, so let's start with some basics. So regarding thermoelectric Seebeck effect. So the Seebeck effect was discovered by the Thomas Jonan Seebeck in 1821. It was actually accidentally found that a voltage existed between two ends of a metal bar when a temperature gradient existed within the bar. So it was not like they were not searching for it. It was accidentally found. The voltage is proportional to the temperature difference. Okay. So this is the alpha AB upon AT. And the other is Peltier effect. So when current I flows through junction of two dissimilar materials, the current I flows through junction of two dissimilar materials, amount of heat over and above joule heat, which has to be removed or absorbed at the junctions to keep the isothermal, is called Peltier heat. Okay, and given by QAB, pi AB, I. It's I or L? I think it's L, no?
I think it's pi IP I only. I think so.
Okay. Yeah, I current.
Pi
Yeah,
IB
yeah,
it's current.
yeah,
Yeah.
I. So when the current I, this is I here, this is here only.
Yes,
The current
yes,
I
yeah.
flows through junction of two dissimilar materials, amount of heat over and above joule heat, which has to be removed, absorbed as junction to keep them as thermal, is called the Peltier heat. And this QAB equals to pi ABI. The Peltier coefficient is related to the Seebeck coefficient by pi AB equals to alpha AB into T.
Absolute temperature. Yeah.
Yeah.
Absolute temperature of junction.
So this is the, like, I think it's important. Maybe there can be a question regarding in your assignment or your exam that how they are related actually. So they are related with the absolute temperature T. So the Peltier coefficient equals to the Seebeck coefficient into T. So this was the thermoelectric module. Okay. So here we can see there is one substrate, okay, that is absorbing the heat. Then there is a copper conductor, there is a p-type semiconductor, n-type, okay, and there is another heat sink, okay? And under there is a ceramic substrate, and there is an electrical connection outside. So in this way you can see the electrons are coming, and due to this temperature difference, because these two junctions are at different temperature, and due to this the electrons are making path through it, and they are going through the external circuit and producing the direct current. This is the thermoelectric TEG. Okay. So for more detail regarding the numerical calculation and derivations, you can refer to the class notes. So this is the thermoelectric electricity and energy conversion. So there is, you can see the p-type, n-type. Okay. So here basically we are okay. So here we are generating the electricity, and here we can see we are providing the voltage to make this difference. Okay. So what is the application to waste heat recovery exhaust gas in automobiles? So this is the exhaust gas inlet and exhaust gas outlet. Okay, in between we can place the TE modules. Okay, and we can generate the electricity. So this exhaust gas is having high temperature. This end will be at high temperature. This end will be at lower temperature. In between, we can arrange the TE modules and we can generate the electricity. This is the stake of a steam power plant. Here also, I think, yeah. So this is a complete power plant. So the various equipment, okay. So this is the stake where the exhaust gas is going through the going to the open atmosphere. So in this part, you can say this part is zoomed here, okay. Where we are putting like hot gas, then we are putting the PNPN materials, okay. This is the other junction. So you can see in this way, we can generate the electricity. So like we can put, so TS is having very wide application. We can put in the stake of steam power plant, we can put in the automobiles, okay. And as I already told you, we are putting it in on the gas stoves, the conventional gas stoves, okay. We can say chulha in Hindi. So we are also putting this on the various things to recover the energy from temperature difference. So now what is MST? It's a magnetohydrodynamic generator. So basically, it is based on Faraday's law of electromagnetic induction. Important, it is based on Faraday's law of electromagnetic induction. So there can be a maybe a match or a question in your exam or maybe an assignment, because like which which technology is connected to which fundamental. Like we have seen Faraday's law, we have seen Seebeck effect, Peltier effect. Okay, so in this there can be a question. So try to remember these or know everything. So when a conductor and magnetic field move relative to each other, an electric voltage is induced in the conductor. Very important statement that when a conductor and a magnetic field move relative to each other, either the conductor is moving in the magnetic field or the magnetic field is moving over the conductor, then there will be an electric voltage is induced in the conductor. Okay. So this is the, you can see the generator. Basically, these are the magnets, and this is the like entry and the exit zone. In this way, we will pass the our high temperature gas molecules. So then gas molecules will ionize. Okay, and there is the magnetic field, and there are some other segmented electrodes are also there. You can see the electrodes are also there. In this way, the EMF will be generated. So there is a diagram of gas conductivity and ionization. Okay. So the gas conductivity is 1 minute. So as the ionization is increasing in percentage, you can see the gas conductivity is increasing. Okay. So some more examples. So yeah. So it uses the hot ionized gas as the moving conductor. So as I told you, the gas will come to the entry point, okay, and move through it, and it will be at very high temperature. The gas molecules will act as a conductor, because at very high ionization, the conductivity of the gas is increases to very high limits. So first gas heated to a high temperature, or you can say very high temperature, around 3000 kelvins. Then valence electrons of the excited atoms move to the higher quantized orbits. So the valence electron will take the energy, and they will excited atoms move to the higher quantized orbits. Ultimately, at certain energy levels, they fly off to become free electrons. So after certain energy level, they like take off from the orbit and they will become the free electrons. Then gas becomes conducting. In this way, the gas will become a conductor. Okay. The normal gas would need very high temperature to reach ionization potential. So hot gas seeded with alkali metal, alkali or metal such as cesium or potassium, and the adequate electrical conductivity of about 10 milliohm, 10 mho per meter can thus be realized at temperature of 2200 to 2700 degrees centigrade. So basically, to provide the needed conductivity, or you can say the needed ionization, we provide the gas, we seed the gas with alkali or metal such as cesium or potassium. Here we can see an example of the MHD in waste heat generation. You can see like this is a steam turbine cycle. Okay, there is a steam turbine. Okay, and evaporator, economizer, etc., compressor, everything is there. But here's the topping cycle. In topping cycle, this section you can see is the MHD. Okay, so this is the MHD duct. You can see this is the MHD duct, and the fuel is coming through here. It will behave. The gas will be in ionization form. There is a magnetic field. You can see the magnetic field. It will generate the electricity, and there is we are having an inverter also. So that inverter is also connected to the steam turbine. We are getting the electricity from steam turbine also. We are getting the electricity from this MST also. So after this gas is going through the to the boiler, evaporator, and economizer to generate the steam. Okay. So first we are applying the MHT. After that, the bottoming cycle. So the steam turbine is in bottoming cycle, and the MHT is in the topping cycle. So in this, you can say that gas will be at 3000 Kelvin. It will go up to 2000 Kelvin. So in this range, we will apply MHD. After this range, till 2000 Kelvin temperature is a very high temperature. So after that, we can apply the boiler and everything else. Okay. And if the company is having enough resources, then they can what else they can apply after 2000 Kelvin? What technology they can apply? I think we have we have TEG, we have MHD, we have TPV. So suppose first we have applied the MHD in the range of this temperature. Now the temperature is at 2000 Kelvin. But still, if we want to generate the steam, so steam can be generated at 1000 Kelvin also. Because 1000 Kelvin is still a very high temperature. You can generate steam easily because for steam, you only need 100 degree centigrade. For superheated steam, maybe for high quality steam, you will require 200 degree centigrade. Okay, but the 1000 Kelvin is very high temperature. So we can also employ the TPV if you are having sufficient resources and you are having sufficient, you can say, the access to the heat available, or you are having some space to put the TPV or system to, or you can connect this TPV to your system. It depends, but still there is a chance. So in this way, we can utilize the maximum waste heat recovery. So there are few points that MSD power output restricted. So at temperature less than 2000 Kelvin, electrons combine with ions to form neutral atoms. So after this temperature, the electron combines with ions. So they will combine with ions and form the neutral atoms. So they will form neutral atoms. So now the gas conductivity will decrease. Gas will not behave as a conductive. The conductivity will become very low, and the MHT will fail because the electrical conductivity becomes very low. Current produced is DC. So it produces DC current. So need an inverter for conversion to AC current. So we need an inverter. Oxide and hydroxide of seeding element cause severe air pollution. So we are also using some seeding element to generate to ionize the gas. So they are creating the severe air pollution. Electrostatic precipitator helps recover the seed for reuse. So we can use electrostatic precipitator. Before before releasing the gas to the atmosphere, we can use this electrostatic precipitator to recover the seed material for reuse. So there is also a other technology, thermionic generator. So thermionic generator, in this we are having a emitter and a collector. Okay? And the thermal energy is coming to the emitter. So this is the direct conversion of thermal to electrical energy. There are two electrodes, emitter and collector. Emitter heated to sufficiently high temperature to emit electrons. So the emitter will basically heated to a very high temperature and will limit the electrons. The collector at a significantly lower temperature receives the emitted electrons. So this collector will receive the emitted electron. This emitter will emit the electrons at very high temperature. The space between the electrons normally filled with a vapor or gas at low pressure. So you can see this space, it will be filled with vapor or gas at a low pressure. And they are both connected through the resistance to the external circuit at where we can generate electricity. So basically this is thermionic generator, now thermophotovoltaic generator. So this thermophotovoltaic generator works on the same principle as traditional photovoltaic PV system. So there is a PN junction that absorbs the optical energy, generates and separates the electron hole pairs to generate electricity. So it's similar to the PV junction. So it absorbs the optical energy, generates and separates electron hole pairs to generate electricity. Different source of optical energy is emission of the photons from an emitter surface at high temperature. What is the difference? So in the PV, we are using the solar radiation, but here we are using the optical energy is emission of the photons from an emitter surface at high temperature. The optical energy we are taking from the photons from an emitter surface that is at high temperature. So the TPU system consists of emitter at very elevated temperature around 900 to 300 degrees centigrade, a photovoltaic power converter, an additional component like filter, concentrator, reflector, etc. There's an emitter that is solid material or engineered surface. Thermal emission characteristics should be the wavelength, polarization, direction tend to be matched to the absorption characteristic of the PV cell to minimize losses. So that should be there should be a like you can say that there should be a match of the properties so that we can minimize the losses. Filters and surface treatment to get selective emission often used for optimization. The efficiency is very low. If when we are saying the low efficiency, it means it is in the range of 10% to 15%, or maybe less than 10%. So due to this, it is ideal for auxiliary power generation from waste heat. It cannot be used for a main power generation, but it can be used as an auxiliary power generation for waste heat recovery. So these are the system for today's class. But still we have half an hour. So maybe we can revise or you can ask something. Varun, Sebas, do you have any doubts?
Sir, for now, no, because the questions are clear.
Yeah, this topic is actually very new for mechanical engineers. Yeah.
Yeah, that's the thing. Mainly that I should cover that MHD so that again I can be into the form again. It's fine.
Yeah, yeah. So anything else, Sebas, from your side? Do you have any doubts? I think Sebas is having some network issue. His voice is not clear. Okay. So we can discuss something. We have half an hour. If you want to discuss anything regarding the energy systems, floor is open. So Varun, basically, in which company you are working? I
So
forget
I'm
the name
working.
actually.
No, I'm working in Tata company. It's like
Tata. Okay.
yeah, it's one of the Tata companies. We design these power plants and all those things. So mainly
So
these
maybe
waste.
you can share your experience like you are designing power plant, you are working in this sector. So it will be good to know your experience like
Yeah, actually I'm
how you can put these waste heat recovery system in your plant actually.
yes,
And
I'm
what current technology
actually
are you using in your systems? Yeah.
yeah. So actually I'm just I'm 1 year. It's like I'm been working in that. It's a new field for me. But today morning only just I'm seeing waste heat recovery. I have seen one of these deaerator storage tanks will be there where you'll be
Okay.
venting out some excess steam. It's like so in that when the outside it's like one vent wall will be there where they have kept a small vent condenser. Okay, it's a small condenser they have kept where it's like the deaerator vendor. He has said that okay, a small condenser should be kept, which will be heating the incoming water which is going into the deaerator again. It's like the deaerator where you have to heat the water and send into we have to send it to it so that at the elevated temperatures we can remove the uncondensable gases or dissolved
Okay.
gases so that the water will be as pure as possible and we can use that water in boiler and boiler for the converting the steam so that the corrosion all these things will reduce for the boiler tubes and everything. So I have seen that it's like a small component where they were not even leaving a small thing anyway. It's like a heat which is being vented out, that is also it's a used heat again. It's like we are
Yeah,
using
yeah.
some steam to heat the water, so that steam also it will be going up as it's low density substance, it will be going up, so they were using that heat also. It's like
Oh,
so I
that's
was thinking it's like many systems are being adopted in that way. It's like they will not even leave small heat anywhere. That's what I thought. But these are the systems which I didn't encounter anywhere. It's like these thermoelectric generators.
yeah, yeah. Actually,
So
these are actually currently if we, the reason behind that the technology is still early stage of TRL. Okay. They are still under
okay.
development, I think, and they are actually costly and the efficiency is also low. So they are very sophisticated also because we cannot put these types of system in like I think the ambient condition should be also like some we have some constraints, I think so. And the cost is also a very main concern. So I think that's why they are used in space industries mostly, or maybe some mm, like only where the other systems are not possible, but still we need some energy.
Yes.
Yeah, yeah,
And mainly, I was really happy that suppose we'll be talking about heat recovery, steam generators, and everything. It's like we'll be talking about why we have to. It's like we'll be using triple pressure heat recovery steam generators, and we'll be telling to the vendor that this is the pinch point we require. So, but I don't know why that pinch point is required. Why we are using three triple pressure generators and all those things. But I'm really thankful that one of our professor in these courses they have explained why pinch temperature is required in a theoretical way. It's like
yeah,
okay, due to the you have to reduce the irreversibility, so such kind of very good concepts which I have learned, and I'm happy that okay, I know little bit why am I using as an engineer, as a mechanical engineer. So we have every for every question we have an answer. So for
yeah,
every action we have a reason for it. So
yeah.
it's
Nice.
like, but the problem is that the field which I am working, the more the questions, the more problems we face. It's like we should go with the flow.
So
it's like
basically, yeah.
as it's not a research field, it's like a consultancy field. It's not a
So,
research field.
so you are directly in the Tata company, or are you in some consultant with some consultant?
No, it's like Tata Consulting Engineers. It's like the company name is Tata Consulting Engineers. So where
Okay,
we
okay.
do, it's like we'll be taking the contracts for the from the overseas also. So we'll be
Okay, okay. So
designing the power
basically,
plants.
you are designing the power plant. Your company is designing the power plant for other vendors. Okay.
Other
So
vendors, yeah,
you,
suppose,
yeah.
yeah,
Okay, okay.
in Dubai or in some of the projects will be there, or Abu Dhabi, all these things. So we'll be
Okay,
taking a
okay.
contract and we'll be designing the entire system. Okay, how many GTs are required, how many heat
Okay,
recovery
it's
steam
good. It's
generators
good.
are
Yeah,
required.
yeah. It's actually very good. I think if you are in the design phase, then it's very good that if you know these old technologies, so maybe you
Yeah,
can
yeah, yeah.
incorporate in the design part also. That's the beauty of this system. Yeah, actually, yeah, you are doing a very good course then. Yeah, I think. Yeah,
Yeah, why? Because suppose if I say that, sir, okay, there is a potential source here, why can't I implement it? I have to do some research work. I have to give the presentation to the client saying
yeah,
that, sir,
correct,
this can be used. So it's an added advantage for us. It's like we are optimizing the system. So it will be added
correct,
advantage
correct.
for me, for the company, and everything. So it's like, but we should properly put that into action. That's what.
Yeah, it's nice. It's nice to hear. So I think you are in your training phase. I think if you are in first year, I think.
No, it's completed. Just recently, I'm complete. Have been okay. My training period is completed.
Okay. So have
So
you allotted the department? In which department you are
yeah,
in?
actually from the 3 months or from the date of joining, just we'll be giving a basic training and we'll be putting into the on job. So that on
Okay.
job only when we have the pressure, so we'll be learning. So we'll be constructing all the process and flow diagrams. So what walls are required, how the steam should flow, what are the pipe sizes for that. So
Okay.
what are the equipment should be there. So
So
nowadays
basically,
it's
you are in the R&D department or like in which
not R,
operation
not R.
department or planning
It's
department?
like
Like
complete. It's like
okay,
process department. So for the power
okay,
plant, so we are the head. It's like the process people will decide. Okay, I want this much megawatt. How many GTGs are required? How many HRSGs are
okay.
required? So
So
it's
are you
like
using some
entire system
modeling software
engineering.
also? Like how are you deciding these things? Maybe you are also using some modeling.
Thermoflow one software is there.
Okay,
It's
okay, okay.
so it's like we can set the configurations. Suppose okay, my GTG is there. I'll be increasing the firing temperatures. I'll be increasing the inlet air temperatures. So what will be
Okay,
my output? So I'll be giving some supplementary firing for the HRSG. What will be my output? So as said in our lecture also, sir said that with supplementary firing we can increase the output. It's like we can increase the efficiency of the plant also in some or the other way. So we can set up a configuration in that software. So we'll be getting the results. Okay, what is the megawatt you're generating? So what is the steam required? So it's like completely
okay.
combined cycle power plants only. This bottoming, topping cycles, all these are every day we'll
So
be using.
basically, I think it's a good point to notice that we can use the software to maybe like to complete modeling of the power plants, I think.
Yes. This is a
Yeah,
very, it's like I feel like this is not basic software I consider. See, as we are a researchers, we'll be using these ANSYS and everything which are completely product oriented. So we are
yeah,
completely inclined towards the product oriented, which will not work in this field. It's like we will be seeing all over the plant. It's like don't go deep into the product. Just know what is that product and why you are using it. Don't go the
yeah,
design
correct.
aspects of the product. So as we are MTech students and research students, we will be more interested into the design field of that product. So which it's like we should be on that top of that. So that's what. So and yeah, we'll be using nowadays. It's like green hydrogen sector is growing, emerging like anything. It's like how we can produce hydrogen and how we can use that hydrogen. So it's like
So
green
anything
hydrogen.
like are you having any projects or companies having any projects to install the green hydrogen plants in India or overseas?
Yeah. No, in overseas they were going on. Overseas, many green hydrogen projects are going, and we are mainly part of that green hydrogen project. It's like completely boom. It's like it's growing like anything. So
Okay.
mainly in overseas, it's going on, not in India.
So are you having any idea if you want to share something?
Actually, green hydrogen, I'm not much familiar with that because I don't have much exposure. Actually, I'm searching for courses of green hydrogen in SWAYAM. I've got one course which is related to chemical engineering. So I have to go through that course, which will be useful for my career also.
Okay. It's on
So,
NPTEL or like where?
yeah, this SWAYAM only. This SWAYAM NPTEL only. One course is like where green hydrogen, how it is going on. It's like it's related to chemical engineering and renewable energy. Renewable energy.
Maybe you can share the name, maybe because this, like anybody else that will be seeing this video later, they can join that course also. If you
Yeah.
remember the name, you can share the name of that
Yeah,
course.
simply you can type in search bar as green hydrogen. So you'll be
Okay.
getting the one course where it's from IIT Bombay. One lady professor, I can't remember her name. She
I
will
think
be
Mr.
telling.
Pratibha. I think Miss
Pratibha.
Pratibha.
Yeah,
Yeah. Okay.
yeah,
Okay.
yeah,
Okay. Okay.
yeah,
Yeah,
yeah.
I know. I know.
She
I
is
know
telling.
her.
Yeah.
Yeah. Yeah. Miss
So
Pratibha. Yeah. Very good professor. Yeah.
yeah, so she is dealing with that green hydrogen course. It's like I suggest if anyone were interested into it, please go through it because it's like a booming technology now. The
Yeah.
entire world is turning into green. It's like renewable energy, how we have to utilize. So it is one of the source where we can use that. So that's what I came to know from the projects which we are doing. And recently we were talking about all these carbon capture technologies and
Actually, yeah,
so
carbon capture technology is also getting booms because we know that we are working to mitigate the climate change issues.
yeah, yeah. So I was going
Yeah.
through some papers now. It's like one of I have got a project where I have to study about the carbon capture and how we can use in our field. It's like
Okay.
so these are the things which are going on mainly. So it's like yeah, one of my senior person has suggested this course. It's really useful for me.
Okay. Okay. Nice. Nice. So where are you posted now? In which state?
I'm in Bangalore now, Karnataka, Bangalore.
Bangalore. Okay.
Yeah,
Okay.
I'm in Bangalore. So it's like and nuclear also good works are going in our company mainly. So it's like they are working on the ITER France. It's like nuclear fusion reactor.
Okay.
Yeah, fusion reactor. The now work is going on ITER France in France. Big project is going on, and where we are part of that. And even I'm very proud to say that even our Chandrayaan mission, TC was one of the part of the Chandrayaan mission. So we have
Okay.
created some
Nice.
of the propellant, how to produce the propellant fuel which is required to that, and the launching pad. We have designed some of the equipments for that launching pad and all those things.
Oh, nice. Nice.
So
Nice to hear this also. Yeah.
yeah, yeah, and Chandrayaan 3 also we are part of that mission. It's like
So it's Tata Consultancy Services, or sorry, Tata
yeah,
Consultant
that's what
Engineers.
actually Tata Consultancy Services is completely software based, and we are
Yeah.
Tata Consulting Engineers. It's like completely mechanical engineering.
Okay.
It's
Okay.
sorry, not
TCE.
mechanical
Okay. Okay.
engineering, completely engineering services.
Completely engineering services. Okay. Consultancy. You are providing. You are having like many field engineers, like different
Yeah,
sectors.
civil,
Yeah. Okay.
architecture, electrical, so whatever required for the power plant, we are there. Whatever required for the architecture
Okay.
base,
Okay.
we are there. So many metro projects also we are taking up. And you know that Ram Ayodhya temple is there, right? Ayodhya Ram Mandir temple. So
Yeah.
one
Yeah.
of
Yeah.
our architecture team has worked on that.
Okay. Nice. Nice.
Yeah, it's going on. Hope so. Career might be good.
Yeah. Yeah. It's good. It's good. Yeah. And if you actually, it's good that you are doing these courses. So you are in a good company, and you are having good opportunity to implement these technologies. Actually. Yeah.
Yes, yes.
So yeah.
Mainly when I was hearing about that pinch point, I was really happy. Why? Because till now I don't know why we are using the pinch point. Now I know why I'm using that. Okay, why have to, any vendor is suggesting this much, what is a pinch point, this much I'm giving, I will not blindly select. I now have a knowledge why he is giving in that way.
So maybe you can share your experience about pinch point, maybe how you can relate the pinch point with your practical application. Yeah, please
So
share
practical
this experience. Yeah.
application. Suppose if we are procuring any heat recovery steam generator. Suppose this is the process how it goes. Suppose okay, we say that this is the heat recovery steam generator. So we decide the pressures. It's like okay,
Okay.
these kind of steams we require, and we require these many steam generators where the steam should go, and these are the extraction points. Everything based from the thermoflow software, we get outputs. Okay, so
Yeah.
using that outputs, we'll be creating some data sheets where we'll be giving the process parameters for that heat recovery steam generator. So that data sheet will be submitted to the vendors. It's like okay, many vendors will be approaching
Okay.
us. So we are
Hmm.
ready to supply to you. So vendor they'll be providing their specification of their equipment where they'll be mentioning the pinch temperature. So
Pinch damage for their
so
heat exchangers. Okay.
their heat exchangers, yes, they'll be
Okay.
specifying their pinch temperatures, and the same pinch temperature also we can use in thermoflow software where it will change the efficiency of the plant. It's like the efficiency also changes. It's like we will be, if suppose heat recovery steam generator is there, some inputs we has to be given in the software. For
Okay.
that, pinch temperature is one of the main input which we have to be, which has to be given. So then only it will say that, okay, based on that, it will do the calculations and it will be giving the output. It's like how much megawatt we are producing. So like entire complete
Okay.
system, it is integrated system. So every single parameter it will be asking. So if suppose 3 to
Okay.
4 vendors, they are giving us offers. So based on
Mm-hmm.
this, okay, we'll be seeing, as you said, as our professor said, pinch temperature is main, which we decide. So the more lesser the pinch temperature, the more will be the costlier the equipment. It's like,
And
because
more will be the efficiency also. Yeah.
efficiency also. So now we
Yeah.
can make a choice, okay, whether I can go with the cost. It's like cost is also a main thing which we will be dealing
Yeah,
with, right?
cost when we are executing a project in real world, then the cost is the main factor actually. Yeah.
Yeah. So that's the way our decision comes there. Okay, it's like if you want to use the rarely it is required to use at pinch temperature, we'll be deciding at
Mm.
that point. So we'll be saying to the client, so this is the thing. If you really want to have that efficiency, we'll go with this heat exchanger, because we know as a pinch point is less, we'll be having good efficiency. So this kind
Yeah,
of
yeah.
some of the good decisions which we can take with this knowledge.
Yeah, it's good. So I request everyone see how Varun is like utilizing this course. I hope everyone will go through all videos from this live session or from the professor's uh, class lectures, so that you can learn more about the energy conservation and waste heat recovery, and you can implement this knowledge to in your professional career, like where you are working, and in future maybe where you will work. So it's good to have this knowledge, because if you are in the energy field, then this course is must for, because because today we are working to reduce the carbon emission, and we have to increase the efficiency for every process. That's why this course is very important. Yeah.
And one
So
more
anything?
thing, if I
Yeah.
speak about this HRSG dual pressure and triple pressure also. So as we are going more and more pressure levels, like triple pressure or like that, so we are coming nearer to our temperature and heat curve. We'll be going nearer to the ideal curve. So that is the reason we are going with the three pressure, triple pressure HRHs. So if you go
Okay.
into that software also, it will be telling the same. Okay, if you, it's many options will be there. Two pressure, single pressure, what you want to choose.
Okay.
So
Okay.
now I will choose three pressure directly, because I know that it will give more efficiency. I don't want to do trial and error now.
Yeah.
So
Okay. Yeah. This is the
such
knowledge.
kind
Yeah.
of, yeah, such kind of small things we can use by this course I understood.
Yeah. Nice. Nice. So it's nice to hear your experience. I think it's great, and maybe many students will inspire from you that
No,
this
actually, I
course.
should get
Yeah.
inspired from you, because you're a postdoc student and you're doing your research, and I really respect research people, because I want to do
Yeah.
research. Even I was more interested into research field, but
Yeah. You can
unfortunately,
actually, no, you can also, like, if you are doing these courses, maybe after working some time, you can do research also. Yeah. Because many students, many postdocs are there after having experience in like company, they are joining some big R&D companies with that experience. Yeah.
yes, that's what even I want to shape my career in that way only. We'll see how it
Yeah.
goes.
Because research is a different thing and practical experience is very different. When you are having both, then it's a deadly combination. Yeah.
Yes. So even my senior mates, they'll be telling, boss, you are poor at handling with the clients and everything, but you are good at calculations and everything. You are good with your concepts.
Yeah.
Because we were into that thing. So I said, okay, let me hold on to this for a few months. Maybe I can, because it's a new field for me, talking with the clients and talking with them and all those things.
It's a good thing. It's good thing. Yeah. Yeah. So you have done your BTech only or masters
No,
also?
I'm a master student. I have done my masters in thermal power engineering,
From where?
NIT Trichy.
NIT Trichy. Nice, nice.
Yeah,
So
I have
yeah,
done
I
my.
think, yeah, I think it's good. Yeah, you can maybe just, if you are still interested in like research, So I advise you that you first take 2 3 real world experience actually how to execute the project and how to implement this thing. After that, maybe you can apply for PhD position and try to uh, apply outside India. Actually, yeah, it will be good.
Yeah, actually, even my mentor and my professor was suggesting that go outside India. It's good. PhDs are very good in outside India.
Yeah,
So
yeah, yeah.
yeah, even I'll see. Even I want to shape my career in that way. Just I'm waiting for an
Because
opportunity.
yeah, yeah, you are having like experience from NIT Trichy, it's good. So and if you are also having like tech professional experience, so I think you will get more weightage in your CV.
Yes, yes, yes. First, yeah, first now I'm just trying hard to get the CV as weightage as possible in that. So doing such kind of courses and everything. I think so. Again, I have a doubt. See, suppose one more course, as I said, that green hydrogen, it's already started in July. As I was unable to cope up with the two courses, I didn't take that course. I think again after these 12 weeks, again
Yeah,
the courses will start.
no, second session will be I think from January next year. Yeah, I think January. Yeah,
Okay, it's like 6 months, 6 months. It's like
6 months,
half
six
yearly
months.
basis. It will start then.
But if you want to really, if you want certificate, then you can join at that time. But if you really want to understand the concept, that course will be available on YouTube also. You
Yes,
can,
yes, yes. I have seen.
yeah,
I have seen. I have seen. It's like if you want to get the knowledge, just go through the things first for now.
yeah, yeah. I think that course is not purely on green hydrogen. That course is basically on hydrogen technology, I think.
Yes, yes, yes. Hydrogen technology, where green hydrogen is also one topic. I think so. I think so.
Yeah, yeah,
I should
yeah.
see the
Green
course
hydrogen will be
content.
there. Yeah, because hydrogen can be generated from many ways. So green hydrogen is the best way to, because today we are focusing on eliminating the carbon. That's why green hydrogen is in focus. But still we are generating so much of hydrogen from other process. The main process from where we are generating hydrogen is steam methane reforming. So basically hydrogen, basically first of all you need to know where we are using the hydrogen. Do you have any idea? Who is the main consumer of hydrogen?
Hydrogen, no, I don't have any idea. That's what I'm completely blank with
Because
that.
yes, suppose we are focusing like for green hydrogen, so but still we need to know like who are the consumers for hydrogen as of presently. So presently most of hydrogen is going towards the like these industries only, steel industries, these refining industries, the fertilizer industry. So they are using hydrogen for their different chemical processes. Okay. So they are
Okay.
using the hydrogen from steam methane reforming. So basically they are using the natural gas, that is a fossil fuel, and they are putting high temperature steam that is around 800 degrees centigrade. So we are having a reactor and we are having some catalyst. So we are putting the natural gas, we are putting the steam, we are making a ratio of carbon to steam that will be around 3 to 1. So with that ratio, we are generating the syngas. Okay, so the CO is also there, the hydrogen is there. Then CO is further reacting in the water gas shift reactor. We are again reacting the CO with the water, and then again we are generating some more hydrogen, and then we are purifying it for pure hydrogen. So this is the way currently we are following. The main drawback
Okay.
for this steam methane reforming is that if you want to generate 1 kg of hydrogen, then you are emitting 9 kg of CO2.
Yes, this one I heard. I heard. I means I've gone through the process, but I didn't pay more attention to that.
Yeah.
Yeah, so 2 to 3 processes were there. Some electrolysis process or something. The steam methane reforming mainly it is used. I think so nowadays.
So 70% of 75% of world's hydrogen is generated from the steam methane reforming. Around maybe remaining 20%, 25% is 20% is around from the gasification, pyrolysis and gasification, etc. And only 4% is from electrolysis. So basically, the electrolysis is the pure green hydrogen. If you like really want to see, because in electrolysis we are just using the water and we are like splitting the water into hydrogen and oxygen,
Hmm.
and we are providing the electricity to split the
Yes.
water.
Hmm.
But still, there is a catch. if you're providing the electricity from your power plant, then it is not green hydrogen. Okay.
Yes, obviously.
So
Yeah, this is the
yeah,
point which we were
directly,
discussing.
yeah, directly hydrogen from electrolysis is not a green hydrogen. Hydrogen from electrolysis, if you are using the renewable energy, like if you are using the wind energy, if you are using the solar energy, okay, then it is green hydrogen because you are using a renewable energy to generate the hydrogen from electrolysis. That's why it's mainly green. Okay, so this is the understanding. So basically, today the hydrogen we are focusing is on green hydrogen. So we are planning to, like all over the world, they are installing this big electrolyzers. So they are like uh, making a hybrid system with solar PV and electrolyzer and all and the PEM fuel cell. So they are like hydrogen economy system we are developing it. So we are planning in our future, we are planning to generate green hydrogen and then use that hydrogen in the fuel cells. Because if you see the fuel cells, so fuel cells are basically the electrochemical device. So they are converting the direct chemical energy into electricity. And the efficiency is very high. Okay. So we can
Yeah.
use the PEM fuel cells in the automobiles for our like for SOFC, like large fuel cells for stationary power generation also. So that's why uh, every industry is like every R&D, every R&D institute, every like research institute, they're all working towards the a hydrogen economy, circular economy, and with hydrogen economy.
Okay.
So that is the point actually, yeah. So I think in India also government is pushing green hydrogen mission a lot. They're providing so much funding. So I hope in coming years there will be so many plants for green hydrogen in India also. Maybe you will be working on one of the plant.
Yeah,
Yeah.
yeah. Wish why because it's like in our office also green hydrogen means it's a bigger thing what they are doing. So compared to the our conventional power plants and everything, so green hydrogen work it will be like going on a very fast pace and more discussions, more sources were keeping where they are pushing into that. So it's like it's yeah, even I'm looking forward to work in it.
Yeah, nice, nice. So they are, I think they are also employing the electrolyzer technology. I think the same electrolyzer technology. Yeah.
Yes, yes, yes.
Okay. Yeah.
So, sir, can I ask you? It's like on which is like what is your research area? It's like
Yeah. Basically, I'm also working on, you can say, green hydrogen and fuel cell.
oh,
Yeah,
okay.
yeah.
So I got the right person then.
Yeah. I am working on like reforming to how to improve the reforming techniques. But I'm not working on electrolyzer sector. I am working on green hydrogen from biomass actually, because biogas is also considered green in the sense that it is still from the west only. So it is also renewable energy. So if we are using the renewable energy to generate hydrogen, that can be called green hydrogen. So we are looking
Okay,
to convert the biogas into green hydrogen.
okay, okay,
So we are using like steam reforming currently, but we are trying to replace it with the dry reforming and some other techniques in which we don't have to put like extra water and all. We can directly react because biogas is basically having the carbon dioxide and the methane, CH4.
okay. So
Yeah.
I'll be really happy if you suggest me any basic textbook or any material to start for the green hydrogen. It's like I'm completely new for that sector. I want to learn something from it. It will be really helpful if you suggest me
Actu-
any.
actually, yeah, sure. So you can note down my email ID.
Yes.
So yeah, it's Amit Sharma 892 at the rate gmail.com. So you can
All are
just put a yeah,
Amit
all in small
Sharma
letter 892
892
892 at the rate gmail.com.
all are small letters, right?
Yeah, all are small letter. So you can put an email. Maybe we can communicate on email. Anybody else
Yeah, sure.
also note down my email ID. If you need any help, you can always email me. no issue. I will be there. So regarding if you are like focusing on green hydrogen, then basically because if you are in TC or like basically you will be working on the electrolyzer technology. So for that technology, we have to see the book. But if you are like for biogas and all, I can suggest. But still, I
Okay.
will find some relevant book and I will share to you.
Yes, yes. At least I want to learn the basics kind of thing where it will be useful for my career later on.
Yeah, sure. Okay, Varun, it's very nice talking to you, and I think your experience is very helpful for this class also. Maybe everybody
Thank
can learn
you.
that with the help of this course, they can apply the course knowledge to work, uh, their work, and also they can improve the like power plants and can do many more things actually. Yeah.
Yeah. Thank
So
you. Thank you.
it's
It's
very
my
good to
pleasure
hear
to
it.
share on this platform.
Okay, thank you everyone. Thank you
Thank you
for
very much.
joining.
Yeah.
I hope I will see you in next class also.
Yeah, sure.
Okay,
Thank
thank you.
you.
Hello, sir.
Hello? Yeah, Sabaz, your voice is not clear, Sabaz, I think.
Sir, due to network issues, sir.
Yeah, please.
Sir, your email ID amitshama892@gmail, sir.
Yeah, let me type it on the chat box. Maybe I can type it on the chat box also. Yeah. It's okay. Can you see the message? Sabaz, can you see the message? Okay. Sabaz, your audio is not clear.
Yes, sir. I'm unable to see the chat box, sir.
Okay, it's AmitSharma892.
Gmail, sir.
Yeah, it's ami@gmail.com.
Okay, sir.
Okay, thank you everyone.
Thank you, sir.
I hope I will see you in next class also.
Yes, sir.
Thank you.